Welcome back to G Fun Facts Online. Today, we are not looking at the stars or digging into ancient history, at least not in the way you might expect. We are looking at a small, unassuming glass vial sitting on a laboratory table. It is a standard 1,000 milliliter container, the kind you'd see in any high school chemistry class. Inside, there is a viscous, pale pink liquid. It looks underwhelming. It looks like strawberry lemonade that has been left out in the sun, but if you were to drop this vial, the loss would be incalculable. Inside this single liter of liquid swims the genetic encoding of 60 petabytes of digital information. To put that into perspective for you, 60 petabytes is enough space to store approximately 10 billion songs. That is essentially every piece of recorded music in human history. The entire Spotify library, the Apple Music catalog, the Library of Congress audio archives, and the private SoundCloud uploads of every teenager on Earth, all swirling in a space no larger than a quart of milk. This is the Atlas Eon 100, the newly announced flagship product from Atlas Data Storage, and as of this week, it has fundamentally changed the physics of human memory. Today, we are going deep into the liquid archive revolution. We are going to explore how we hit the limit of silicon, how biology solved the storage problem 3 billion years ago, and whether we are truly ready to trust our history to a molecule that can be destroyed by a splash of household bleach. To understand why this pink liquid is such a massive deal, we first have to understand the stupidity of our current situation. We are living through what experts call the data apocalypse. For the last 40 years, the digital world has been built on a concept called planar scaling. We make things smaller, and we make them flatter. We etch billions of transistors onto 2D silicon wafers. We coat miles of plastic tape with magnetic particles. We spin aluminum platters at 7,200 revolutions per minute. This approach gave us the smartphone and the cloud, but by the early 2020s, the cracks started showing. The primary issue is density. A modern hard drive is a miracle of engineering, but it is mostly air and metal housing. The actual data storage layer is infinitesimally thin. If you walk into a server rack in a data center, those humming, blinking monoliths that power the internet, 99% of the volume is wasted space. It is cooling fans, power supplies, plastic casing, and the air gaps required to keep the machines from melting. Then, there is the energy problem. In 2024, data centers consumed roughly 2% of the world's total electricity. By late 2025, driven by the voracious appetite of generative AI models, that number had crept toward 4%. We are literally burning coal and natural gas just to keep our digital memories from fading. And fade they do. We are facing a longevity crisis. Hard drives have a life expectancy of 3 to 5 years. Solid-state drives lose data if left unpowered for a few years. Even LTO magnetic tape, which is currently the gold standard for archiving, only lasts 30 years. And that is only if you keep it in a room with strictly controlled humidity and temperature. 30 years is a blink of an eye. As Dr. Elena Kogan, a synthetic biologist at the forefront of this movement, put it, we were building libraries out of sand. We were desperately stacking sandcastles while the tide of data was coming in. We needed a medium that wasn't just denser, but eternal. Enter the molecule of life, DNA. DNA, or deoxyribonucleic acid, is fundamentally a coding language. It doesn't use the binary zeros and ones of computers. Instead, it uses a quaternary code of 4 chemical bases: adenine, cytosine, guanine, and thymine, A, C, G, and T. The density of DNA is difficult to comprehend. A single gram of DNA can theoretically store 215 petabytes of data. Visualizing that is hard, so think of it this way. You could store all the data currently on the entire internet, every tweet, video, email, and website, in a shoebox full of DNA. But theory is one thing. Practice is another. The road to the Atlas Eon 100 has been paved with slow, expensive failures. The modern era of DNA storage really began in 2012. That was the Rosetta Stone moment. Harvard geneticist George Church encoded a 53,000-word book into DNA. It was a proof of concept. It was incredibly slow, and it cost a fortune, but it worked. The book was recovered with 0 errors. By 2016, Microsoft had entered the game. They purchased 10 million strands of synthetic DNA from Twist Bioscience. They weren't just storing text anymore. They were storing deep archival data, managing to encode "This Land Is Your Land" by Woody Guthrie and a high-definition video by the band OK Go. But the problem was always cost and speed. In 2020, writing a few megabytes of data into DNA cost thousands of dollars. The process used chemical synthesis, building the DNA strand molecule by molecule, which was a toxic, slow process involving harsh solvents. It was like trying to write a novel by carving each letter into stone. The breakthrough that led to the Atlas Eon 100 wasn't in storage capacity, but in the writing process itself. This was the enzymatic revolution of 2024 and 2025. Bill Banyai, the founder of Atlas Data Storage, calls the shift from chemical synthesis to enzymatic synthesis the Gutenberg moment for DNA. Instead of forcing molecules together with harsh chemicals, scientists engineered enzymes, biological catalysts, that could build DNA strands naturally, just like the cells in your body do, but at super speeds. While chemical synthesis took 3 minutes per base and created toxic waste, enzymatic synthesis takes milliseconds per base, is water-based, and can create strands over 10,000 bases long. This is what makes the Atlas Eon 100 possible. It is not just a container. It is the result of a new manufacturing process that prints DNA fast enough to make it commercially viable. So how does it actually work? How do you get 10 billion songs into a liter of pink liquid? It happens in 4 steps. Step 1 is translation. The digital file, let's say an MP3 of Bohemian Rhapsody, is broken down from binary into the quaternary code of DNA. 00 might become A, 01 might become C, and so on. But it is not that simple. DNA hates repetition. A long string of As causes biological errors. The DNA strand folds up or breaks. So algorithms randomize the data, adding error correction codes similar to those used in QR codes. This ensures that even if a few strands break, the song can still be played perfectly. Step 2 is synthesis, or the write. This is where the Atlas machine hums to life. Millions of microscopic nozzles deposit enzymes that grab nucleotides from the air and stitch them into strands. This creates the liquid archive, a soup of trillions of floating DNA fragments. Each fragment has a barcode on the end, an address label telling the computer where this piece belongs in the larger file. Step 3 is preservation. This is the crucial Atlas innovation. DNA in water can degrade if it gets too hot or is exposed to UV light. To solve this, the Atlas Eon 100 uses encapsulation. The DNA strands are trapped inside microscopic silica glass beads or metallic capsules suspended in the liquid. This protects the data from the elements. According to the founders, you could boil this liter of liquid, and the data would survive. You could leave it in the desert for 1,000 years, add water, and still play the Beatles. Finally, step 4 is retrieval, or the read. To play a song back, you don't play the liquid. You take a tiny pipette drop, a microliter. Because of a biological amplification method, called PCR, you can use enzymes to search the liquid. You introduce a primer that matches the barcode of Bohemian Rhapsody. The biology ignores the billions of other songs and only copies the strands associated with Queen. These copies are then run through a DNA sequencer, a device now the size of a smartphone, which reads the letters, converts them back to binary, and voila, the music plays. However, Atlas Data Storage is not alone. The year 2026 is shaping up to be the war of the archives. While DNA conquers density, other technologies are fighting for the crown of durability. While Atlas plays with liquid, Microsoft has bet on solidity with Project Silica. They are storing data in quartz glass, using femtosecond lasers that pulse for a quadrillionth of a second. They etch 3D voxels into plates of glass the size of a DVD. The capacity is about 10 terabytes per glass square, but the durability is over 10,000 years. The advantage here is that it is write once, read many. You cannot accidentally delete or hack the data once it is etched in glass. It is physically permanent. In 2026, Microsoft is already using this for Azure Cold Storage, storing sensitive government archives. Then there is the ceramic challenger, Cerabyte. Out of Germany, this startup uses a ceramic-on-glass technology. They etch data into nanolayers of ceramic, creating something akin to microscopic QR codes that are fireproof, floodproof, and EMP-proof. Their pitch is simple: data on ceramics. It sounds ancient, like Sumerian clay tablets, and that is the point. Ceramics last forever. So how do these compare? DNA wins on density. Nothing beats it. You can hide an entire data center in a perfume bottle. It is perfect for deep cold storage, data you might not need for 100 years, or data you need to smuggle. But glass and ceramic win on access speed. Reading a glass plate is faster than sequencing DNA. They are better for warm storage, data you might need to access once a month. The 10 billion songs claim is a great marketing hook, but the reality of what is being stored in these liquid archives is far more profound. As of 2026, we are seeing some incredible artifacts encoded into DNA. The Arch Mission Foundation has already placed DNA archives on the moon, containing the English Wikipedia and linguistic keys to 5,000 languages. If Earth falls, the backup is literally on the moon. There is also the Global Music Vault, buried deep in the permafrost of Svalbard. It uses silica glass to store master-quality recordings of indigenous music, ensuring the songs of vanishing cultures are never lost. We are even seeing the DNA of things. Manufacturers are mixing DNA into the plastic of high-end products. Luxury watchmakers are embedding DNA certificates of authenticity directly into the metal casing of their watches. And in a darker twist, researchers have successfully encoded a computer virus into a strand of DNA. When the gene sequencer read the DNA, the software processing the data executed the code and crashed. It was a stark warning. Biological data can hack digital systems. The elephant in the room, of course, is price. In 2020, storing 1 megabyte in DNA cost $3,000. Today, thanks to the Atlas Eon 100's enzymatic process, that price has plummeted to roughly 1 cent per megabyte. That is still expensive compared to a hard drive, but for archival data you have to look at the total cost of ownership. A hard drive costs money to power and cool every hour of every day, and you have to replace it every 5 years. A DNA capsule consumes zero energy. It takes up zero space. It needs no maintenance. Over 50 years, DNA storage is now cheaper than hard drives for data that doesn't need to be read often. So where do we go from here? If 2026 is the year of liquid archives, what does 2030 hold? The frontier is in vivo storage. Right now, the Atlas Eon 100 uses dead DNA in a test tube. But scientists are working on encoding data into the genomes of living bacteria. Imagine a colony of E. coli in your gut that stores your medical passwords. Imagine a tree whose leaves contain the history of the land it grows on. This is not science fiction. Researchers have already used CRISPR to edit a GIF of a galloping horse into the DNA of living bacteria, which then multiplied and passed the GIF down to their children. The movie survived for generations. We are moving toward a world where the cloud isn't a server farm in Virginia, but a biological slurry in a vat, computing and storing data with the efficiency of life itself. As we look at the Atlas Eon 100, we are forced to confront a philosophical question: what is worth saving? When storage was expensive, we had to curate. We chose which photos to keep. When storage becomes infinite, when 10 billion songs fit in a liter, we lose the filter. We will save everything. Every bad take, every surveillance video, every embarrassing moment. The right to be forgotten may become the defining legal battle of the late 2020s, not against Google, but against the very molecules we use to store our lives. But for now, there is something poetic about the loop closing. Life began as information encoded in DNA, floating in a primordial soup. Billions of years later, intelligent life has learned to encode its own music, its art, and its history back into that same soup. The liquid archive is not just a storage device. It is a message to the future, written in the language of life, saying, "We were here, we sang these songs, and we found a way to make them last." Thanks for listening to G Fun Facts Online.